Good morning, afternoon, or evening. Today I'm gonna be going over a little bit of logic with you. I'll be going over proof by contradiction. All right, that is the goal. So let's jump right into it. So naturally, naturally, it is easier for us to notice problems than it is for us to notice solutions. All right, now if you think about it, this is true. This is just a fact of human nature. If you let's say you got in your car tomorrow morning, and for whatever reason the car didn't start, you would notice that. Now, noticing a solution to that problem is not gonna be as easy. I mean, unless you're a licensed mechanic or something. Noticing a solution to that specific problem is not necessarily going to be easy. Uh, you're a lot more likely to notice the problem itself than you are to notice the solution. If noticing solutions was so easy, then people wouldn't pay hundreds of thousands of dollars to hire problem solvers. But we can use this fact of human nature to our advantage. The fact that humans, by nature, we notice problems quicker than we notice solutions, and that's essentially what proof by contradictions do. Proof by contradiction, it takes advantage of your ability to notice problems uh, quicker than you can notice solutions. So I'll keep going, explain some more. For example, oh, here's a slide of the example that I just gave. If your car broke down, would it be difficult for you to notice? No. No, it would not be difficult at all for you to notice, not unless you are indeed a licensed mechanic. Same thing I just said. Would you agree with that? Moving on. Moving on. When proving things, by contradiction, what you are doing is taking advantage of your natural tendency to notice problems more easily than you notice solutions. Okay? All right. When proving things by contradiction, what you are doing is taking advantage of your natural tendency to notice problems more easily than you notice solutions. Same thing I just said, just a reiteration, just to give you a visual. I don't know, maybe some people could be deaf watching this, so I like to write out the things that I'm saying as well, not to be redundant. All right. So how do you do such a thing? How do you use your natural tendency of noticing problems to help you in a mathematical proof? Let's see. Let's see. All right. The goal when proving conjectures or theorems, by contradiction is to show that if the hypothesis of your conjecture or theorem is true, but the conclusion of your theorem is not true, then you encounter some sort of problem. Another word for problem, contradiction. That's where the word proof by contradiction comes from. Thereby leading you to conclude that if your hypothesis is true, then your conclusion is also true as well. Okay, so in proof by contradiction, what you're gonna do is all right. So conjectures and theorems, they have hypotheses and then they have conclusions. If and then everything that follows after the if is your hypothesis, and everything that follows after the then is your conclusion. What we do is we assume our hypothesis to be true, but our conclusion is not true. And we basically just continue to operate under the assumption that our hypothesis is true, but our conclusion is not true. We operate under that assumption, and we show that eventually, after continuously operating under that assumption, that we encounter some sort of contradiction. And when we do encounter that contradiction, that then thereby leads us to conclude that if our hypothesis is true, then our conclusion must also be true. Okay? The reason is we operated under the assumption that our hypothesis is true, but our conclusion is false, and we came into some sort of contradiction. Well, if something is mathematically true, it'll never create a contradiction. And so if something does create a contradiction, we conclude that it's not mathematically accurate. And so if we conclude that when our hypothesis is true, and if we conclude that if hypothesis is true, but conclusion is not true, if we conclude that that leads to a contradiction, then that must not be true. The entire, that the fact that the hypothesis being true, but the conclusion not being true, that can't be a true statement. So we must be able to conclude that if hypothesis, then conclusion, which is exactly what we want to prove if we're trying to prove a conjecture. All right, I'm gonna go to the next slide. I'll be working with a specific example to kind of tie everything together. All right, so here's the example. So I got my conjecture, and my conjecture is if you multiply a rational number m by an irrational number q, then the product will also be an irrational number p. Okay, so I got two numbers, m and q. M is rational, q is irrational. And I want to show, my goal is to prove that m times q is equal to some other irrational number. My goal is to show that the product of a rational number and an irrational number is equal to an irrational number. So here I have my hypothesis written out. Hypothesis. Multiply rational number by irrational number. If I multiply a rational number by an irrational number, then I get this conclusion. Product is irrational. All right. So this is my hypothesis. I got my hypothesis written out, and then I got my conclusion written out. So what I'm going to do is, in order to prove that this is true, I want to prove that this is indeed true. My goal is to prove that this is true. If this, then this. That is my goal right now. But the strategy that I'm going to be using proof by contradiction. So in order to prove that this is true, what I'll be doing is assuming that this is true and this is not true. Okay. I'm going to assume that my hypothesis is true, but my conclusion is not true. And when I do that, I'm gonna run into a contradiction. And so that contradiction tells me that it must not be the case that this is true and this is false. Okay? It must not be the case that this is true and this is false. Thereby concluding that it is the case that this is true and this is true simultaneously. Okay? All right. So moving on to the specific example. Hopefully, if it's confusing for you right now, hopefully it won't be after I go on and show you this example. All right. So, proof by contradiction. Proof by contradiction. Assume hypothesis is true, but conclusion is not true. This would mean, all right, if I assume that my hypothesis is true, but my conclusion is not true, this would mean that m times p equals q, where q is not rational, i.e. q is not irrational, i.e. q is indeed rational. So basically, what I'm assuming right now is that m times p, I'm assuming that rational number times irrational number equals rational number. And I'm going to show that that leads to a contradiction. Okay. All right. So let's keep moving forward. M times P equals Q. All right. if I apply a little bit of algebra, I get P is equal to Q divided by M. All right. Now, keep in mind, I'm operating under the assumption that my hypothesis is true, but my conclusion is not true. And in other words, I'm operating under the assumption that M and Q are both irrational. Rational. M and Q are both rational. That's the assumption that I'm operating under. I'm operating under the assumption that rational number times irrational number equals rational number. So that means Q and M are both rational. All right. Now, what would that mean? If Q and M are both rational, then that would mean that Q over M is also rational. All right. I got a rational number divided by another rational number. There is no way to divide a rational number by another rational number and not get a rational and for the quotient to not be rational as well. So just to reiterate that, I feel like I said it a little confusingly. I can't take a rational number and divide it by another rational number and not get and the quotient of these two not be rational. Okay, there is no way for that to happen. This must be rational. All right. Now, well, what does that mean in the grand scheme of things? All right. If Q over M is also rational, but remember what we said P was. We said that P was irrational. How can you have a rational number? How can you have a rational number P equal to an irrational number Q over M? That is the contradiction that we were looking for. You see what happens when we assume that our hypothesis is true. When we assume that our hypothesis is true, i.e., M is rational and P is irrational, but our conclusion is false, i.e., Q is rational. When we assume that, we get this contradiction down here. That's the contradiction we run into. The contradiction is irrational number being equal to rational number. That can't happen. That's a contradiction. Therefore, what we do is we conclude that it cannot be the case that M is rational, P is irrational, and Q is also rational. It cannot be the case. So what is our alternative? The alternative is that M is rational, P is irrational, and Q is also irrational. That's the alternative. But when you think about it, that is exactly what we were trying to prove in the first place. We were trying to prove that if you take a rational number and you multiply it by an irrational number, then you get an irrational number. And we just convinced ourselves that indeed must be the case. All right. So proof complete. That's the example. That's a quick example of how proof by contradictions work. Now, one thing that I do want to mention is when is proof by contradiction applicable? When are we able to prove something via contradiction? Well, all right. That's an easy question to answer. You can prove something by contradiction anytime you know enough about your conclusion to be able to spot a problem within it. Okay? So going back to the previous example, I know enough about rational numbers. I know enough about rational numbers and irrational numbers to be able to spot a problem, such as the problem that we came across here. Such as this problem. If this is irrational and this over here is rational, that is a problem. Now, if I didn't know enough about rational numbers and irrational numbers to be able to spot that problem, I would have never noticed the contradiction. Now, and that makes sense. I mean, if you're trying to prove something about Z-lofts and you don't, if you're trying to prove something about Z-lofts by contradiction, you would need to be able to identify a problematic Z-loft from a perfectly fine and functioning Z-loft. Z-loft is a word that I just made up off the top of my head, but that's, it still serves the same purpose. If you want to prove by contradiction, if you want to do a proof by contradiction about something, you need to be able to be familiar enough with that thing to where you can spot a problem where you can spot a contradiction when you come across that contradiction. All right. So that's proof by contradiction. And that's that's all I have. Hopefully this video was helpful for you. If it was, feel free to subscribe and leave comments. Constructive criticism is welcome. So that's all I have. Good luck to you and all your mathematical endeavors, and have a good night or day or afternoon, wherever it is for you. Right now is night for me, but have a good morning, afternoon, or night. Peace.